Hi everyone. Previously, in this lecture series on Schmidt triggers, we looked at how to realize the Schmidt triggers at circuit level using op amps and resistors. Now, in this lecture, we will see how to realize Schmidt triggers with asymmetric transfer characteristics or asymmetric threshold voltages. Now, what do I mean by asymmetric thresholds? Now let's look at the inverting and non-inverting Schmidt trigger transfer characteristics, which we discussed in the last two lectures. Shown here is the voltage transfer characteristics of an inverting Schmidt trigger, and shown here, this one is the voltage transfer characteristics of a non-inverting Schmidt trigger. Now if you observe the Schmidt trigger characteristics, you will immediately notice that the low to high and the high to low threshold voltages obey a relationship. What is that relationship? Your low to high voltage, in this case this is high to low transition voltage, and this guy will be your low to high transition voltage. You can see that your low to high transition voltage is simply equal to minus of V high to low transition voltage. That is, the transfer characteristics exhibit some kind of symmetry around the origin. The points where the transitions happen, they tend to be equidistant from the origin. You can explain the same thing here as well. So here if you see beta Vsat plus beta Vsat happens to be your low to high threshold, and minus beta Vsat happens to be your high to low threshold, and it will obey this similar relationship. Your low to high threshold will be a negative of the high to low threshold voltage. So that is, the magnitude of low to high and the high to low threshold voltages will be same. Okay, I mean they are same in the architectures that we have discussed so far. The voltage transfer characteristics show this condition, they exhibit this condition. So this is what I mean by symmetric threshold voltages. Now what if I want to have a voltage transfer characteristic where this condition is not satisfied, where your low to high threshold voltage magnitude is not equal to the high to low threshold voltage? So that is, I can have this transfer characteristic shifted slightly towards right or towards left. In that case, your high to low and low to high threshold voltages will not be symmetric or equidistant from the origin. So those characteristics, I'm going to call them as asymmetric threshold voltage or asymmetric Schmidt trigger characteristics. The question is, how do we realize that? And even before that, an even more important question is, why do we need these asymmetric thresholds at all in the first place? In this lecture, I'll try to answer all these questions. So first, before we start realizing or looking at how to realize asymmetric threshold voltages, first we'll understand what is the significance of these threshold voltages. I mean, what impact does these threshold voltages have on the output waveforms of Schmidt triggers? Now you guys should recall what is the main purpose of a Schmidt trigger. A Schmidt trigger is mainly used for converting sinusoidal signals or ramp signals to square wave outputs. Okay, so usually your sinusoid and ramp signals, they will either the points where they cross zero or the threshold voltages, their slopes will be very small. Okay, so their slopes will be very small, or they will rise very slowly or fall very slowly. When you pass them through a Schmidt trigger, the output of a Schmidt trigger is going to be just a square pulse. And if you see, for a square pulse, the edges will be very sharp. So you can see a Schmidt trigger as a circuit which is like an edge sharpener. It's going to sharp your edges. Okay, it can be, for example, if I just directly pass this through a comparator, let's assume a open loop comparator with a zero crossing detector. Okay, then what am I going to get? I'm just going to get a square wave where the rising edges of these square waves will match with the zero crossing of this waveform. If I pass it through a Schmidt trigger, those rising and falling edges will happen at a slightly different voltages. But the end outcome is going to look the same. I mean, it's going to be looking like a square wave with very sharp transitions. Okay, so that's the purpose. Now let's look at what impact does these threshold voltages have. So let's assume I'm going to feed a waveform, a periodic waveform, whose average value is 0, and it exhibits some kind of symmetry around the x-axis, the time axis. So I've already used this word called odd symmetric. Okay, odd symmetric. So anytime I talk about periodic signals, if I use the word odd symmetric, in your mind you should picturize like this. You just take the periodic signal. So usually for any periodic signal, if you understand how the waveform looks like in one single cycle, then you have understood the waveform for all time. So you can just cut the waveform for one single cycle and observe it. Now let's assume the waveform is going to look like this. So if you cut your waveform for one single cycle and just observe this, you can choose any point in this interval 0 to t. You can choose any point in this interval 0 to t. Around that point, if the waveform obeys this condition, f of t should be equal to minus of f of minus t. If the waveform obeys this condition, then I'm going to say it's an odd symmetric waveform. The waveform exhibits odd symmetry. I'm going to use that word. Okay, so if the waveform obeys this condition, and if you integrate the waveform over one cycle, the average value will be 0. Okay, since you can choose one point around which it's going to obey this condition, it's going to have a positive half cycle and a negative half cycle, and the area under the positive half cycle will exactly cancel out the negative half cycle's area. Okay, if it obeys this condition, the average value will be 0. And also additionally, such waveforms will only contain odd harmonics. If you plot its Fourier transform, Fourier series, it's a periodic signal, so we'll plot Fourier series, it will only contain odd harmonics. So keep this in mind. Anytime I say I use the word odd symmetric, in your mind you should picturize the waveform in one single cycle, and then it should exhibit odd symmetry, which means it should satisfy this condition around any point in the time period. You can pick some point, and around this point, if it obeys this condition, then you can argue that the waveform is odd symmetric. Okay, so that's something to keep in mind. So here I have assumed a waveform which is odd symmetric, which means its average value is 0. And if you observe this waveform, right, so if you see, this is one half cycle, and this is one full cycle, and this is one half cycle, and this here is one half cycle. The slope of the signal in the rising edge cycle, where it is increasing, in this one half cycle it is decreasing. The slope of the ramp waveform is same in both these half cycles. Okay, so this waveform clearly exhibits odd symmetry. Now if I pass this waveform through a Schmidt trigger, let's assume I'm going to pass it through a non-inverting Schmidt trigger. What kind of an output should you expect at the output of a Schmidt trigger? So I'm passing this through a non-inverting Schmidt trigger, which means if your waveform is increasing, if it crosses plus beta Vset, just look at this graph. If your input signal is increasing, if it crosses plus beta Vset, your output will become plus Vset. So at this point, when your input crosses plus beta Vset, your output will go to plus Vset. Before that, it is going to be at minus Vset. It will stay put at plus Vset till the output decreases once the input starts reaching a peak value, and then it will start decreasing and decreasing and decreasing. Then at this point, when your input crosses minus beta Vset, that will be your high to low threshold. At that point, your output will go to minus Vset, and it will stay put at minus Vset till the output reaches plus beta Vset. The input crosses plus beta Vset. So if you observe this waveform, you are getting a square wave output with very sharp edges. And what is the duty cycle at the output? That duty cycle will be 50%. Okay, the duty cycle is 50% because your waveform exhibits odd symmetry. Its average value is 0. And the threshold voltages are symmetric. It is plus beta Vset and minus beta Vset. So if you find the time between plus beta Vset and minus beta Vset, between this point and this point, you can clearly see that it will be t by 2 seconds. Therefore, I can argue that the on time will be t by 2 seconds. And similarly, the time between this point and this point here is again t by 2 seconds. So therefore, this waveform is going to exhibit the output waveform will have 50% duty cycle. So that's the take home point here. The threshold voltages control the duty cycle at the output of your Schmidt trigger. Now it will become clearer to you if you assume that, let's look at a waveform which doesn't exhibit odd symmetry, which means during the during the rising edge cycle where the input signal is constantly increasing, it's increasing with a smaller slope, but it is going to decrease with a faster slope. Okay, remember it's a periodic signal, which means it's repeating at this is your entire time period. The point where the signal reaches from let's assume this is minus V peak and this will be plus V peak. The point where it starts from a negative voltage, the negative peak voltage, and reaches the positive peak voltage, the time it takes. Previously it was 1/2 cycle, now it's greater than that because it's increasing slower in 1/2 cycle. So it's going to take more than t/2 seconds. So which means the waveform is not purely symmetric. It doesn't exhibit odd symmetry. And if I pass it through a Schmidt trigger with symmetric threshold voltages, meaning with the threshold voltage obeying this condition, V low to high will be equal to say beta V sat, and V high to low is equal to minus beta V sat. I'm assuming a non-inverting Schmidt trigger. For a non-inverting Schmidt trigger, you can see here the low to high threshold will be positive and high to low threshold will be negative. Okay, so if I pass it through this Schmidt trigger, what would you expect? What you should expect is that at this point, when it is reaching plus beta, when your input reaches plus beta V sat, your output will go to plus V sat. It will remain at plus V sat till the output goes lower than minus beta V sat. Now if you make a quick observation, right, this duration, the point where the waveform goes from plus beta V sat to minus beta V sat will be less than t/2. And from minus beta V sat to plus beta V sat, from this point to this point, this duration will be greater than t/2 seconds. Okay, so therefore your output waveform's duty cycle will not be 50%. The on time will be smaller than t/2 seconds. Therefore your duty cycle will be less than 50%. Right? Your duty cycle is on time by total t on upon total time period times 100. That's your duty cycle. So because you can clearly see here from so here the falling edge is faster. It's falling much faster in this half cycle. It's falling much faster, but it is increasing at a much slower rate, which means it's going to spend much longer time in the positive half in the rising cycle. Therefore, this threshold from, if you measure the time distance between minus beta V sat to plus beta V sat, that time will be definitely not equal, will be greater than t/2. So off time will be greater than t/2 and on time will be less than t/2. So duty cycle will be less than 50%. So in such cases, in this case, I cannot have, if it turns out that my input waveform doesn't exhibit odd symmetry, which means its average value is not 0 here, in that case, having symmetric threshold voltages doesn't really help me. In that case, I would prefer to have asymmetric threshold voltages. Okay, I would want to have an asymmetric threshold voltages. So let's assume this transition point at this point happens to be at some voltage. I'm going to call that as VLH. Okay, let's call it VLH, which I'm going to call it as beta 1 V sat. Okay, it's proportional to V sat, but it's not exactly the same beta. I'm going to call it some beta 1 V sat. Beta 1 is less than 1. Now the high to low threshold point, I don't want it to be at minus beta V sat. Instead, I will start from this point, draw a line and find the time at which it reaches t/2 seconds. Okay, I'll find the time at which it reaches t/2 seconds, and then that will be I will ensure that, so it can be slightly at an increased time, at this point. This will be my new threshold voltage. If I ensure this as my new threshold voltage, then I will get 50% duty cycle. So if I have an input waveform which doesn't exhibit an odd symmetry, which means its average value need not be 0. In that case, having asymmetric threshold voltages can give me a 50% duty cycle. That's the significance of having asymmetric threshold voltages. Okay, I'm taking some example, one simple example here, where there is no, asymmetric, having asymmetric threshold voltages. So just look at it this way. This is the point where you have set your low to high threshold voltage. Now move t by 2 seconds away from that point. Okay, and then if you choose this point as your, which is actually t by 2 seconds away from the low to high threshold, this is your high to low threshold point. Okay, then you can guarantee your on time is t by 2 seconds. If your on time is t by 2 seconds, this is a periodic signal, so your off time will also be t by 2 seconds. So my new threshold voltage, where the transition is going to take place, will happen at a slightly, I'll show it on a different color, will happen at a voltage which is not symmetric, which is not negative of the high to low threshold voltage. So that's the advantage of going for asymmetric threshold voltages. If I can somehow realize asymmetric threshold voltages, then even if I know the input waveform is not going to have exhibit odd symmetry, I can guarantee a 50% duty cycle at the output. Okay, so that's it. So summarize quickly, threshold voltages help you in setting the duty cycle at the output of your Schmidt trigger. Therefore, and choosing the threshold voltages asymmetrically can give you 50% duty cycle, even though your input waveform doesn't exhibit odd symmetry. Okay, it's not symmetric around the time axis. Okay, the zero line, So that's the advantage. So now we will see how to realize those how to realize an asymmetric asymmetric transfer characteristics or asymmetric threshold voltages. So to realize asymmetric threshold voltages, in your mind you should think that I need to have two different feedbacks, beta 1 and beta 2. For low to high and high to low, I cannot have the same feedback factors. I cannot have same beta Vset. That beta Vset was the feedback voltage previously. I cannot have same feedback voltages for low to high and high to low thresholds. And how do I achieve that? I can just put two different resistors and put two different diodes with opposing polarities. Okay, I can just flip the direction of the diodes in two different paths. So which means if your output is plus Vsat, one diode path will turn on and your feedback factor will be different. And if your output is minus Vsat, the other diode will turn on, okay, and your output will, your feedback factor will be minus some other beta 2 times Vsat. So that's the whole idea behind this. So we'll analyze this circuit. So here I'm first starting analyze. I'm just showing you guys an inverting Schmidt trigger architecture, which can realize asymmetric threshold voltages. So I have two resistors, Rx and Ry. Of course the values are different, and now I'm going to put two diodes with differing, with opposing voltages, opposing polarities. I've just flipped the diode in one path, and then I'll be able to turn on two different paths for two different threshold voltages. So again, whenever you are analyzing a Schmidt trigger circuit, I've always said start with input voltage being much smaller than 0. Okay, input value, we can assume theoretically it's a huge negative value, which is less than minus Vsat itself. Okay, Vsat is this is a op-amp based circuit. I'm going to assume the maximum positive voltage in circuit is plus Vsat, minimum voltage is minus Vsat. So we can assume that your input voltage is even less than minus Vsat. If your input voltage is a huge negative voltage, what will happen to this? This is an inverting comparator, so output would have been at plus Vsat. So this is what it will be. Output will be at plus Vsat. Input now is at less than minus Vsat. The feedback voltage will be plus beta Vsat. Now if you can see this, your inverting terminal is at a huge negative voltage, non-inverting terminal is at a positive voltage, so output will stay at plus Vsat comfortably. There is nothing to change its state. Now if you see, this diode will turn on and this diode will be cut off, right? For a diode to turn on, the anode voltage should be greater than the cathode's voltage. So this node voltage should be greater than this. This node voltage is at plus Vtest. That's the highest voltage here. The other end is connected to ground. So obviously this diode will turn on. This will be cut off. So the path that is active will be through resistor Rx. I'm assuming for simplifying the analysis, it's an ideal diode with zero cut-in voltage. So the feedback factor is going to be, the feedback voltage at the non-inverting terminal will be plus beta 1 times Vsat, where your beta 1 is given by R by R plus Rx. So now I'm slowly increasing my input voltage from minus Vsat. I'm slowly increasing it. The moment your input voltage exceeds plus beta 1 Vsat, your inverting terminal voltage will become greater than the non-inverting terminal voltage. Therefore, your output will go to minus Vsat. So that's your high to low threshold. So as I'm increasing my input voltage, when my input voltage exceeds plus beta 1 times Vsat, the output will go to minus Vsat. So the threshold the high to low threshold voltage is beta 1 times Vsat. Now, after this point, when your input exceeds plus beta 1 Vsat, so I'll show this here. Now my input has exceeded plus beta 1 Vsat. Output has now gone to minus Vsat. If your output has gone to minus Vsat, what would happen to this circuit? Your diode, let me name this as D1 and this diode as D2. Diode D1 will be cut off because now your anode is at the lowest voltage, which is minus Vsat. Okay, so this diode D1 will be cut off and D2 will be active. So if D2 is active, I'm going to end up in a situation like this. The resistance Ry will be now in the feedback path. Rx is now open. That's no longer in the feedback path. Now remember, your input voltage is greater than beta 1 times Vsat, which means it's a positive value. It's a positive value which is greater than beta 1 times Vsat. Now the feedback voltage is minus beta 2 because now the feedback path is through Ry. The feedback factor beta 2 will be R by R plus Ry. The feedback voltage is negative, but it is not negative of the beta 1 Vsat, right? It's some other voltage. It is beta 2. The feedback voltage now is minus beta 2 times Vsat. So now if you see here, right, this node voltage is negative, which is minus beta 2 times Vsat, and the input voltage is positive. It has already exceeded beta 1 Vsat. Now I'm increasing it further. If I increase it any further, the output will comfortably stay at minus Vsat because the non-inverting terminal is at negative voltage and inverting terminal is at a positive voltage. So output will be at minus Vsat. It will stay put at minus Vsat. I'm showing this graph's progression at this point. So even if you increase your input voltage greater than beta 1 Vsat, your feedback voltage is negative. So therefore your differential input to the op-amp will always be greater than 0. Your differential input to the op-amp will always be less than 0. V minus will be greater than V plus. So your output will stay at minus Vsat. Now, once I've increased my input to minus Vsat, now I'll slowly start decreasing my input. Remember, the feedback voltage is minus beta 2 Vsat. So as I keep decreasing my input voltage, when my input voltage goes lower than minus beta 2 times Vsat, okay, when Vin becomes less than minus beta 2 times Vsat, that is when this op-amp, the comparator's output will change its polarity. At that point, your V plus will become greater than V minus because your V minus is just the input voltage itself. It has gone to a lower negative value than V plus. So then your output will go to plus Vsat. The moment your output goes to plus Vsat, V plus will become positive and V minus is already negative to begin with because that's the input voltage itself. Your input voltage is negative. It is in this region. So V minus is negative, V plus is positive. So therefore your V minus will be less than V plus and output will stay comfortably at plus Vsat. Okay, I'm sorry. At this point, when your input exceeds Yeah, when your input exceeds minus beta VSAT, your output will become plus VSAT, and the feedback voltage will now become, I'm sorry, here the feedback voltage now will become, I think I should, let me redraw the circuit here. So at this point, see, until this region, when you are in this region, as you are decreasing your input, the feedback voltage is minus beta 2 times VSAT. That's the feedback voltage. Okay, therefore the transition happens at minus beta 2 VSAT. When your input voltage exceeds, goes lower than minus beta 2 VSAT, your output will go to plus VSAT. The instant your output transitions to plus VSAT, the feedback voltage will now be beta 1 VSAT, plus beta 1 VSAT. Okay, it will become positive. So your V plus will become positive, which will be plus beta 1 times VSAT. So your resistor Rx will be now turned on. That's the path that will be turned on, and RY path will be cut off. Okay, diode will be off, so that path will be disabled. Now your input voltage is, to begin with, it has already become negative. It has already gone lower than minus beta 2 VSAT. So V minus is negative, V plus is positive. Therefore, you can clearly say that the output will stay put at plus VSAT. So that's what is shown here. It's staying put at plus VSAT. So now we have the characteristics that we can draw here. So you can clearly see the high to low threshold voltage happens to be at plus beta 1 VSAT, and your low to high threshold happens at minus beta 2 VSAT, and this graph is no longer symmetric. Okay, it's the, if I move on either directions, the transition points happen at asymmetric. I mean, they don't happen at negatives of each other. They are no longer symmetric around the origin. Okay, so that's how I realize a non-inverting Schmidt trigger with asymmetric threshold voltages by just using diodes. That's one way of realizing it. Similarly, I can apply the same principle and then take an inverting, what I've shown here is an inverting Schmidt trigger characteristic. Okay, similarly, I can do the same thing for a non-inverting Schmidt trigger. Remember, I should only alter the feedback path. Okay, so in the feedback path, I'm going to use two resistors instead of a single resistor, so that I can alter the feedback factors. See, the feedback factor depends upon the polarity of the output. I'm just going to make it dependent on the polarity of the output, right? If you guys recall, the threshold voltages depend on the output voltage. Now all I need to do is just change the feedback factors for the high to low and low to high thresholds. How do I do that? Just put two different resistors and connect diodes. Diodes will guarantee that, because diode can only carry current in one direction, it will ensure only one of the paths is turned on. Okay, so that's how I can guarantee asymmetric characteristic. Again, you can start analyzing the same circuit. Now that we have analyzed that circuit in detail, I'll quickly analyze this. Always start with a huge negative voltage. I have written minus infinity here, but you can assume Vi is minus VSAT. If Vi is minus VSAT, this is going to the non-inverting terminal voltage. So you can see that this output voltage will go to minus VSAT as well. Okay, so if your output voltage is at minus VSAT, this diode will be turned off and this diode will turn on. So your path which will be active will be through Rx. So if your output is at minus VSAT, input is now at a huge negative voltage, and now I'm slowly starting to increase it. So the voltage at the non-inverting terminal, we have already derived this, will simply be superposition, right? Vi into Rx by R1 plus Rx. So here I'm assuming the diode cutoff voltage is 0, cut-in voltage is 0. So I'm ignoring, there is no V gamma in the expression. V gamma is diode's cut-in voltage. So I can just assume V0 is minus VSAT and write this voltage. So it will be Vi into Rx by R1 plus Rx minus R1 by R1 plus Rx. Okay, that's VSAT into R1 by R1 plus Rx. You just have to find out the condition where, as I am starting to increase my input, at some point the V plus right now is at this voltage, V minus is now at ground, is at 0 volts. If you see, input is negative, output is negative, so therefore this node voltage is nothing but superposition of two negative voltages. This will also be negative. Okay, V plus is negative right now. We just need to find the point when V plus becomes greater than 0. So that I'll just take this and equate it to 0, and the point where it happens will be R1 by Rx. So your beta 1 in this case will be R1 by Rx, and when your input exceeds beta 1 times Vsat, your output will go to plus Vsat. So when your output goes to plus Vsat, the other diode will turn on, the path Rx will be cut off. So now if you see, your input voltage is positive, right? We see your input voltage has reached V low to high threshold, which means your input voltage has exceeded beta 1 times Vsat. Output voltage is also plus Vsat, it is also positive. So this node voltage will be positive. V plus will be greater than 0. So output will stay put at plus Vsat. Okay. So let's assume this is the point where the transition happened, beta 1 times Vsat. So after this point, the feedback factor will be different. But all I'm trying to say is that even though the feedback factor is different, this node voltage will be positive. Therefore, output will stay put at plus Vsat. So any increase in this direction, output will be at plus Vsat. Now if I'm slowly starting to decrease my input, from plus Vsat, I'm slowly decreasing my input voltage. Then all I need to do is find out when this node voltage goes less than 0. So this node voltage V plus, once the output has gone to plus Vsat, will simply be given by this. Apply superposition, it will be Vi times Ry by R1 plus Ry plus Vsat times R1 by R1 plus Ry. Just equate it to 0, or just use this condition. When this goes to less than 0, your output will transition. So the point where it transitions will be minus of R1 by Ry times Vsat. So that's your high to low threshold. So now you can immediately see the transition voltage from high to low is not the same as the low to high transition. So that's how I achieve asymmetric characteristics. So this is the transfer characteristics. So I mean, once you transition to minus beta Vsat, it's going to stay put at plus Vsat. You can verify that yourself. So this is the transfer characteristics of a non-inverting Schmidt trigger. And how do I realize asymmetric threshold voltages using diodes and resistors? Okay, I've shown the schematic and its equivalent transfer characteristic with all the threshold voltages written here. Okay, so once I know how to realize asymmetric threshold voltages, I can now use this circuit if I know that the input waveform doesn't exhibit odd symmetry, and if I tell you specifically I need a 50% duty cycle at the output, then you can use this circuit. Okay, having a symmetric threshold voltages may not yield 50% duty cycle. In that case, you may have to go for an asymmetric threshold voltages. Now the next question is this the only way we can realize is this the only way we can realize asymmetric threshold voltages? The answer is no. We can realize in other ways as well. One quick way, I mean, if let's say mathematically I just tell you guys I want to realize asymmetric characteristics, what can you think of? I'll just take this character. I'll start with an let's start with a symmetric characteristic. Let's start with this. Let's assume this is minus beta Vsat. Let me just show. So let's start. Assume that we have symmetric characteristic. If I can somehow right, so if I can somehow shift these characteristics, so on this, so I'm first assuming that both the transitions are happening symmetrically around the origin. Okay, now I'm going to take this characteristic and show you guys. So assume that initially it was symmetric. If I can shift it in this direction or this direction, okay, by some constant fixed factor, fixed number, then I can achieve asymmetric thresholds. Okay, previously we were changing the factor beta itself. Now I'm suggesting that we can keep the beta factor the same, but if I can somehow add a fixed offset voltage to the threshold values, if I add a negative value, I can push it in this direction. If I add a positive threshold offset value in this direction, I can push it towards the right axis, I mean towards the positive x-axis. Okay, so I can do that. So that's the idea. So how do we add offset voltages? The way in which we add, so first we'll start with a non-inverting Schmidt trigger characteristics, is to use, instead of connecting this node to ground, I can simply connect it to some voltage Vref. Okay, I'll connect it to Vref. Now we'll see what is the feedback quantity. Previously, when this was connected to ground, the feedback quantity was what? Beta times Vsat, or plus or minus Vsat. Now it is going to be beta times Vsat. Beta here is R1 by R1 plus R2. Okay, that's the feedback factor in this case. Now the voltage at this point will be beta times V, or I'll write it as in terms of V naught. V naught can be plus Vsat or minus Vsat. It will be beta times V naught plus R2 by R1 plus R2. I can just use superposition to show this. It will be R2 by R1 plus R2 times Vref. So now this R2 by R1 plus R2 can be written as 1 minus R1 by R1 plus R2. So therefore I can write it as 1 minus beta times Vref. Now the feedback voltage is this, beta times V naught plus 1 minus beta times Vref. So your V naught can be plus Vsat or minus Vsat. It doesn't matter. Okay, if it is plus Vsat, you are still adding this constant factor to it. If it is minus Vsat, you are still adding this constant factor 1 minus beta times Vref to it. So what will happen? Your low to high and high to low threshold voltages, both are getting added a factor of 1 minus beta times Vref. So that's what I've shown here. The graph here, I'm just adding, take the existing Schmidt trigger architecture, okay, with symmetric threshold voltages, and instead of connecting this node to ground, I just need to add a fixed offset voltage to the feedback factor. How do I add that? By just connecting a voltage source at this point, some voltage Vref. Okay, I'll again later take some design examples and show you, how do you derive Vref. It will be more useful when we start analyzing single supply systems. You'll see how very simply you can do that. Okay, so that's the idea. So I'm not analyzing this circuit. I'll leave it to you guys. It's very simple. All I'm showing you here is that the low to high and high to low thresholds usually happen whenever your input, which is connected to the minus terminal, exceeds V plus, or it goes lower than V plus or higher than V plus. And so I just need to find out, I just need to add a fixed voltage, fixed offset voltage to V plus. So this, whatever be the polarity of V naught, whether it's minus Vsat or plus Vsat, you are going to add this fixed voltage of 1 minus beta times Vref. And that has an effect of adding a fixed offset voltage to both the positive, the high to low threshold and low to high threshold. I'm adding the same voltage. So that has this effect. We just discussed before itself. So this is an inverting Schmidt trigger. So if I start assuming that this was at minus beta Vsat, if I add a positive Vref, the graph is going to shift in this direction. Okay, if I ensure that if I ensure 1 minus beta times Vref is exactly equal to, say, minus of beta times, plus beta times Vsat. If I ensure this, then what will happen? The low to high threshold will be equal to 0. I can make the transition happen at 0 volts. If I ensure that this is greater than beta Vsat, the low to high threshold voltage will entirely be positive. In fact, your graph would have been shifted in this direction. Okay, I'm sorry, you get the picture, right? I can shift this graph to this point. So here I'm ensuring that if I satisfy this condition, 1 minus beta times Vref to be greater than my plus beta Vsat, then this term minus beta times Vsat plus 1 minus beta times Vref will be greater than 0. So which means your low to high threshold voltage will become positive. I can have that as well. Okay, so you'll later see when we talk about single supply systems how all these things will be. You will see that how all this will be very useful in building Schmidt triggers for single supply systems. So this is another way. That's by adding a fixed offset, you can again realize asymmetric threshold voltages which are not symmetric around x equal to 0. The 0 axis, the 0 point on the transfer characteristics. In the same way, if I want to add an offset to the non-inverting Schmidt trigger, I can do that by connecting some threshold voltage at the inverting terminal. So let's look at this circuit. What have I done here in this circuit? So remember, previously for the non-inverting Schmidt trigger, the non-inverting voltage V plus is given by what? You can apply principle of superposition at this node. It will be Vi times R2 by R1 plus R2, and the feedback factor due to the output voltage will be V0 times R1 by R1 plus R2. Okay, so and if you guys recall, previously assume that this node voltage was connected to ground. This node voltage was connected to ground. Then your V plus can be written as Vi plus beta times V0, the whole thing multiplied by R2 by R1 plus R2. That used to be the voltage if the inverting terminal was connected to ground. Okay, that's the, sorry, even now it is the same. It is V plus, and V minus used to be 0. Previously it used to be 0. Now if I see, if I connect this, if I connect a resistive divider and voltage Vref, V minus is given by R2 by R1 plus R2 times Vref. So the total differential voltage Vd, which is V plus minus V minus, is given by this. Okay, I'm just taking R2 by R1 plus R2 common out and subtract these two voltages. This voltage minus this voltage, you will get Vi plus beta V0 minus Vref. So remember, anytime a comparator's output is changing, either your differential voltage, if your Vd is greater than 0, your output will go to plus Vsat. If your Vd is less than 0, your output will go to minus Vsat. Right? So I don't even have to analyze the circuit. The transitions happen when your input voltage is greater than or equal to minus beta V0 plus Vref. So I can take this. The transitions will happen whenever your Vd is either greater than 0 or less than 0. Okay, so or I can translate in terms of Vi. You can just take this term, equate it to 0, and you will get this. If your Vi is greater than minus beta V0 plus Vref or less than minus beta V0 plus Vref, you will have a transition. It will either be a low to high or high to low transition. So if your V0 is plus beta Vsat, V0 is plus Vsat, then the threshold voltage will be, the high to low threshold voltage will be minus Vsat plus Vref, minus beta Vsat plus Vref. And if your V0 is minus Vsat, the threshold voltage will be plus beta Vsat plus Vref. So again, I'm not analyzing the circuit. All I'm trying to show you here is that previously, if your Vref was connected to ground, the transition points used to happen when you are satisfying this condition, when Vi is greater than or less than minus beta V0. Okay, then your output will go to plus Vsat or minus Vsat. Okay, now instead of this, the transition happens at a point minus beta V0 plus Vref. So I've added a fixed offset voltage to the characteristic. So that's what I've shown here. Okay, so by adding a fixed offset voltage, I can realize asymmetric threshold voltages. So far we have discussed how to realize asymmetric threshold voltages, and first I'm going to draw for inverting Schmidt trigger. For an inverting Schmidt trigger, there are two ways in realizing that. You can either use diodes, okay, in the feedback path. So this will ensure that the low to high and high to low threshold voltages are different. Okay, or you can ensure that the feedback factor is same. Here the feedback factor itself is different for the low to high and high to low threshold voltages. Here I am keeping the feedback factor the same, R2 and R1, but instead of connecting this node to ground, I will connect it to a fixed voltage. I am just going to add an offset voltage to both the low to high and high to low threshold voltages, and in that way I am realizing an asymmetric transfer characteristic. Okay, and for this, the same thing happens for non-inverting Schmidt trigger. For a non-inverting Schmidt trigger, this is what I've shown here is inverting Schmidt trigger. For a non-inverting Schmidt trigger, if you want to ensure that, if you want to get asymmetric characteristics, Either I should ensure that the feedback factor is different for the different transitions, or I should add a fixed offset. Okay, so here in this case the feedback factors are different for different transitions, or the other way of doing adding fixed offset is I can simply add it to this terminal. Instead of connecting this to ground, I'm just connecting it to some other voltage. Okay, I'm keeping this at R2 R1. This is Vi, this will be R2 R1 and Vref. So remember, in this case I've shown you guys one way of realizing adding an offset. You can think of other ways as well. You can actually add offset directly to the input path itself. You can start with this architecture. Say this is R2, this is R1. I can create another path. Okay, and let's call this also R1. So this path will be Vi and this path will be at Vref, and I'll ground this. Okay, so this will also lead to a similar characteristic but with some polarity changes. So you can try it yourself. The non-inverting voltage, in this case you should apply principle of superposition. Again, the analysis will be little bit more different than what we have done before. So you will have to, when you're applying superposition, you will have to take the factors are going to be little bit complicated. That's it. Okay, but you can analyze it yourself. I'll leave that to you. But all I'm trying to tell you is that I put same resistance R1 here. I can have it different as well. I can have a different resistor value, or I can have R1 as well. You can analyze this circuit and derive the values. In this case, what will happen is that the threshold voltages will be whatever, some beta times V naught. It will be minus a factor of Vref. Okay, instead of plus Vref, it will be minus Vref. That's the only difference here in this architecture. Okay, so if you apply positive Vref, you will be shifting your graph. Your graph will be shifted in this direction. Here, if you add positive Vref, you are shifting in this direction. That is this architecture here. You will be shifting it towards the right. The transfer characteristic will shift towards the right. Okay, this graph will shift towards the right. If you connect the offset voltage at this non-inverting terminal, okay, some additional reference voltage, the effect is similar. The final outcome is that you will be creating an asymmetric characteristic, but now instead of shifting it to right, you will be shifting it to left, because if your Vref is positive, you will shift it to left. If your Vref is negative, you will shift it to the right. Okay, so I'm not analyzing this circuit. I'll leave it to you. It's very simple to analyze this and write the expressions and analyze it, but I'm just showing you guys the different ways in which one can realize asymmetric threshold voltages. Okay, in the next lecture we will go on to analyze Schmidt triggers with single supply systems, and then I'll also, since some of you have asked for what happens, how do I build Schmidt triggers with open collector or open drain outputs, I'll discuss all that in the upcoming lectures. Thank you.